In example 14.2, we are asked to find 3 different member forces, and only 3, in this truss bridge that has a tension counter in the middle panel. Right? The tension counter business just means it's a member that can only handle tension. It's something that is usually addressed at a different lesson. Here, because the 3 members we want are not going to be influenced by the tension counter situation, I'm not going to get into those details. The other thing that you're provided are the reactions A, which turns out to be the only reactions we really need. But we've shown, as is typically the case where you're not given reactions, a review about how to find those, and even a check to make sure, as we sum forces in the vertical direction, that we did our math correct, and sure enough, that worked out. So we're starting with reactions. We've got these 3 members. They all happen to be connected to the same joint. And so note that one of the members we want is right connected to joint A. That's this support one. And that might be a really advantageous thing, because note, if I work a free body diagram here, I only have 2 unknown member forces. Again, the applied force is, at least in terms of the structure, it doesn't know it's actually a reaction and responding to the applied loads. It's just a force sitting here. And so I have 2 equations, 2 unknowns. I can solve for those 2. Check mark. That's good. If I come up to joint G, notice I got 1, 2, 3, 4 forces, one of which I now know. But hey, you know, if I only knew BG, then I'd have 2 equations, 2 unknowns to find the final 2. And I can go to joint B to find that pretty easily. So bam, I already know I got a relatively easy path here to do the analysis. So we're going to go to joint A first, and we're going to show our free body diagram. I usually don't initially show the member forces until I can figure out what's going to happen by intuition. So there's your reaction of 124 going up on the joint, and that means with only a diagonal has a vertical component, it has to be coming down to have a vertical downward component, and that's AG. And that means it has a leftward X component, so that means AB has to be acting to the right. And even though we don't need AB to do the work here, we're still going to show it for completeness sakes. Right, now, if you pay attention to the geometry of the truss, we've got 18-foot wide panels, and we have 24-foot high panels. So that turns out to be one of those beautiful 3, 4, 5 triangle kinds of situations that's going to make our math a little easier to process, of course, as we go on through this. Some forces in the Y, let's take up where it's positive, we get 124 minus, well, we want the vertical component, so 4/5 of AG. That's all going to equal 0, and therefore we find out that AG is going to be equal to 5 divided by 4 times 124, or 155. Let's make sure that's right. 5 divided by 4 times 124 is 155. Okay, so that was the correct number. It turned out to be a positive. Right? All forces are going to be in kips, so I'm not going to keep writing the units right now. And that is shown in compression. So bam, we've got that one. Right, so now we go and we, for completeness sake, so I'm going to do this anyways. Some forces in the X, I'm going to get in 155 as a minus times 3/5, then plus AB is equal to 0, and therefore we'll find out that 155 times 0.6 is 93, so therefore AB equals 93, and that will turn out to be in tension. Right? I'm just going to want to verify that math again because I've done this math earlier, got a slightly different number, and so let's just check one more time. 124 times 5 divided by 4 is 155. Looks good to me. Take it times 0.6. Yeah, still, we run the math every time and it looks like that. We'll find out soon enough whether or not this is going to work out, right? Then we get, let's go to joint B. And at joint B, then we've got a T-joint. That makes this almost trivial. We do have an applied load at the T-joint of 80 kips. We've got what we just found out was AB at 93. we've got BC, which by sum of forces in the X is also going to be 93. And we've got BG acting upwards. And this is really actually kind of trivial here. Sum of forces in the Y. We've got then BG minus 80 equals 0. Therefore, we're going to have something simple there. Sum of force in the X positive. We'll get 90 minus 93 plus BC equals 0. And therefore, and now we switch colors, and we find out that, of course, BG equals 80. It's shown in tension, and that BC is equal to 93 in tension. We, again, don't really need those numbers, but at least the horizontals, but we're doing for completeness sake. And then we can go to joint G, and we'll have then 4 members framing in. We've got the end post at 155 in compression. Remember, we got to turn that around. It's in the members in compression, so it's got to be pushing on the joint. The vertical is in tension at 80, so it's pulling away from the joint. And then we have CG, which we don't know yet, but I'm going to say I do know that I have 124 of the vertical component of AG, so that's 155 that we had is acting upwards, right? At 124 minus the 80 coming down, I have a net upwards. CG has to be going downwards. And since I have 2 rightwards forces, that means that top chord GH has to be acting to the left. That means it's going to be in compression, which is kind of what I've anticipated anyways. And so note what's going to happen here. We're going to have, let's see, we'll have to do sum of forces in the X first. No, we don't. We do sum of forces in the Y first. Why? Because we only have one unknown component in the Y. So I'll have 155 upwards times 4/5. That's our 124. Minus the 80. Pull, let's see. Yep, minus 80. Minus CG times 4/5. So it's 124 minus 80. Right, that was 124 was the vertical component of that. And then after setting that equal to 0, and then multiplying through times 5 divided by 4, we get 55 for CG. And once again, we got a positive number, that means we get right. And it's pulling away from the joint, so it's in tension. Then we're going to do sum of forces in the X. Let's take the left positive. We get GH minus 155 times 3/5. Right, that horizontal leg minus our 55 that we just found times 3/5 equal to 0. So we'll have a net of 210 times 0.6. For that fractional value, and we find out that GH equals 126 in compression. We will find out in another lesson how we can do this with method of sections. And that would both provide a check, but it also turned out that the sections might be very fast for some of these member forces.